Welcome back to our lecture series on remote sensing. Today we're gonna talk about image resolution. Last lecture we talked about what are the characteristics of remote sensing image, and we have an idea what is a remote sensing image now. I told you earlier there's a certain difference between the terms of picture, image, and photography when it comes to remote sensing. So today we're gonna talk about what is the image resolution. So simply image resolution when in remote sensing is defined as the ability to render information from a remote sensing image at the smallest discretely separable quantity. So in other words, resolution can be told as the ability of a system to render information at the smallest undividable quantity. In terms of there are four terms according to each resolution, each type of resolution. One is distance, in terms of distance, wavelength band of electromagnetic radiation, and also time and radiation quantity. So here there are four types of resolution we're gonna discuss. One is spatial and spectral, radiometric, and temperal. I told you earlier there are this undividable quantity is measured in a term based on four terms: distance, wavelength, and time, and also radiation quantity. So here ground or spatial resolution deals with the distance, term of distance, and wavelength deals with spectral resolution. I'm going to explain it later. Radiometric deals with the radiation quantity, and also temporal resolution deals with the time. So when it comes to these types of resolution, let's have a basic rough look on these types. So spatial resolution is the based on focus on the size of the field of view. Actually, when it comes to 1 pixel, whether it's smallest area we can take on to a remote sensing image from the ground is described through spatial resolution. And spectral resolution refers to the number and size of spectral regions the sensor records data. Examples we can see blue, green, red, or near infrared, which wavelength region this which wavelength region of the electromagnetic spectrum this image belongs to. And also temporal resolution describes the way how often the sensor acquires data. So this deals with the repetitivity of the sensor. So when a sensor covers the same area after quite a certain time, then we describe its temporal resolution according to the period of time. So radiometric resolution is not quite described in many references I referred. So the sensitivity of detectors to small differences of electromagnetic energy simply can be defined as the radiometric resolution. So let's look further about these types of resolutions. First let's talk about spatial or ground resolution. It actually spatial resolution is the ability to distinguish close spaced objects of an image, or otherwise you can say size of smallest dimension, or surface over the independent measurements which can be made by the sensor. That's called spatial resolution. In other words, we can say this is the ground segment sense an instant. So this is determined by the size of IFOV. It is IFOV stands for instance field of view, instantaneous field of view. It refers to the corresponding field of time at a certain moment. So field of view means maximum angle of view which sensor can effectively detect. The electromagnetic energy comes from the surface. So instantaneous field of view means the angle which corresponds with the sampling unit at the time. So I guess this is how spatial resolution can be found. The height has to be multiplied by the instantaneous field of view. Then you will have the ground resolution element, or in other words, spatial ground resolution or spatial resolution of the sensor. So here you see the size of area on the ground that sensor sees at any point of time is called spatial resolution, or more accurately, every time a single signal is captured and determined with the help of IFOV. If the function is given their cone angle multiplied with the height of platform, which is called h here. Cone angle beta is multiplied with h, and then IFOV can be found. The minimum distance between two objects that the sensor can record distinctly is the spatial resolution. So quite it can be described in many ways. So let's move further. So here the higher the spatial resolution is, the smaller the ground resolution cell, and also when the spatial resolution is high, the resolving power of the system is also high, and also much spatial detail can be attained. So to discriminate a feature from its surroundings, we can call that there should be least as large as the ground resolution cell. So we can be sure that it can be detected with a certain resolution. And also the spatial resolution can be refers to the smallest unit of area that can be measured in, which indicates the objects that can be detected. So here we spatial resolution, we're gonna find spatial resolution based on this measurement. So IFOV is the cone angle of visible of the sensor, or in the other words I told you earlier, the maximum angle of view which a sensor can effectively detect on electromagnetic energy comes from the surface. So it is called FOV. So instantaneous being stood by I. So instantaneous field of view means angle which corresponds to the sampling unit. So you have to keep in mind. So FOV means the maximum angle of view which sensor can effectively detect, and also instantaneous field of view means with the angle which corresponds in sampling units at a certain time. So B stands for here to determines the area of that relevant to given altitude. So area viewed can be measured. B is equal to altitude multiplied by IFOV. So that value is called ground resolution cell or ground resolution element, GRE or GRC. So it can be found, in other words, the height to the platform multiplied by IFOV. So you can see also, if you want to have a screenshot on formal definition of spatial resolution and how this equation is built up, you can have wait. And there are some problems with this concept. One is, unless height is known, IFOV will be changed. So h changes from platform to platform. So we need to specify flying height to determine resolution. So we can't say we know for sure this platform is in this height of certainty. We can calculate the spatial resolution, otherwise we can't. So it's also generally okay to spaceborne instruments and stable orbits only. And IFOV and GRE have to be known, ground resolution elements, and instantaneous field of view has to be known. These have to be known parameters to calculate the spatial resolution. So this is the same. This is an illustration of instantaneous field of view, geometrical illustration. So if you want to have a look, you can see how it's illustrated geometrically. And how these equations IFOV and GRE is defined formally here. And to define that, it's a moral question. To answer this, you have to have an idea about which broom, scanners, and I'm not going to describe it in here. We will talk about scanner in a whole another lecture. So if you wanna have a look at this same GRE is found IFOV multiplied by the height of the platform. These are some additional formulas for you. So here you can see, here 1 meter spatial resolution means 1 pixel represents 1 meter square. So you can see from 1 meter area to 1 square, so much details can be obtained here. So this is called a high resolution image. Even the 1 meter resolution, 2 meter resolution, 5 meter resolution, 10 meter, 20 meter, 30 meter, you can see when the resolution number gets meter value gets high, image get blurred, because here 1 meter resolution means this represents 1 pixel in 1 square meter. Here this pixel can see maximum value of area that 1 pixel can obtain is 4 square meters. Here 25 square meters. Here 900 square meters. So what you think the high resolution is? Of course, the 1 meter resolution, because 1 pixel can show you detail of a 1 square meter on the surface. Here you can see through 1 pixel only 900 detail on a 900 square meters area, so you can have an idea when the spatial resolution is high and when it is low. So the resolutions of today's satellite system vary from few centimeters to kilometers. So lower resolution usually coincides with a higher repetition rates, meaning that within a short interval, such as assume that 15 minutes, the satellite reflects same area. So we talk about this repetitivity of a sensor when it comes to the characteristics of satellites later. So there are plenty of characteristics of a satellite. So one is satellite repetitivity time, and so we'll talk about that later. And I mentioned about this repetitivity before that. I think when I described about scan line in characteristics of remote sensing image. So coarse resolution is used to record large or global areas for climate related inquiries. For example, the radiation budgets of the Earth and for weather monitoring. Additional applications include Earth observation of land use and oceans, the ocean's ice cover, and surface temperature. So Rayleigh criterion is used to for these measurements. So it's something when the objects are just removable if maximum center of the distraction pattern one falls on the first term, minimum of the distraction pattern on the other. So these are some additional stuff. So the smallest resolvable angle can be found in this equation. So what is Rayleigh's criterion? These are some additional stuff and resolving power. Satellites with medium resolution, as an example, Landsat 7. So if you want to, there are different types of satellites. So passive satellites, Landsat is a passive satellite system. So there are Landsat, Cartosat, and so a bunch of satellite systems, passive and active both. So when it comes to active, ERS system comes to in my mind. So if you want an explanation about these satellite systems, so leave a comment. So as I was explaining, medium resolution such as Landsat 7 are used for the global observation of land surfaces, and tropical rainforest and their deforestation have been observed by Landsat satellite for more than 30 years by using medium resolution images. So high resolution data is mainly used for small areas of Earth's surface. Only recently such as has become available commercially and privately. Satellites such as Iconos and QuickBird send data for the topographic and thematic map of the example of the land use, vegetation, or planning resources for the city, large projects, etc. Information can be ordered in advance, because simply in turning the satellite sensors can reduce the repeat rates, and that can monitor desired areas earlier. So that's about spatial or ground resolution. Then let's move to spatial resolution. You can see to spatial resolution 30 meters, 50 meters, which can image has a better spatial resolution, or image on the left with having a glance. You can say that even without mentioning the resolution values. So difference of the scale of two images you can say also. So this is something to think, how the spatial resolution and scale of image compare. And for remote sensors, the distance between target being image and the platform plays a large role in determining the detail of information and the total area imaged by the sensor. Then comes to spectral resolution. Before that, you have an idea about electromagnetic spectrum. We discussed widely about this, how the electromagnetic radiation scatters and how its wavelength depends on visible range according to each color, and also in IR region, near infrared to far infrared, and UV region, and all the things we have discussed earlier when it comes to ERM. So spectral resolution is basically the ability to resolve spectral features and bands into their separate components. In other words, it describes the ability of sensor to define wavelength intervals. So the finer the spectral resolution is, the narrower the wavelength and the range of a particular channel or band can be detected. So spectral resolution required by the analyst or researcher depends upon the application involves, of course. So different classes are featured in when it comes to spatial resolution. Broad classes, according to the application we use, if you want to separate some vegetation area, we have to add a specific classes, or for when it comes to geology, assume there's a rock type we need to observe through remote sensing image, so we have to require finer wavelength ranges according to our need. So sensor with higher spectral resolution is required for detailed distinction. And also when it comes to spectral resolution, it deals with the location with or sensitivity of chosen wavelength of band. So in other words, ability of sensor define fine wavelength intervals. So, and also finer spectral resolution is the narrower the wavelength ranges, as I told you earlier. Then we can say that finally spectral resolution describes the ability of sensor to define fine wavelength intervals, so which has the fine spectral resolution, black and white film or the color film. So multiplex, when it comes to spectral resolution, we have to talk about two types of sensors, multispectral and hyperspectral. So multispectral sensors deals with limited number of bands. It collects data at select wavebands or channels. Many remote sensing systems record energy over several separate wavelengths, which ranges at various spectral resolution when it comes to multispectral resolution sensors, and also they record energy over several wavelength ranges and various spectral resolution. And also, spectral resolution of a sensor refers to the number of locations of spectral bands. Then comes to the hyperspectral sensors. When it comes to hyperspectral sensors, advanced multispectral sensors is another word used for hyperspectral sensors, which detects hundreds of narrow spectral bands to visible range or IR range or infrared portion of electromagnetic spectrum. So high spectral resolution always deals with fine discrimination between the different targets based on their spectral resolution in each of narrow bands. So then we comes to radiometric resolution. So radiometric resolution, before that I would like to say about something about spectral coverage. What is a spectral coverage? So spectral coverage is the total wavelength range observed by the sensor. So it can be done by spectral measurements. So there are many kinds of spectral measurement devices, such as stereoscopes, spectroscope, spectrometer things. So spectroscope is used for human eye observations of human eye observations of the spectrum. So, and also spectrometer is to record spectral reflectance, and monochrometer to read single narrow bands, spectrophotometer for photometry, and also spectroradiometer for measurements of spectral radiations. Then we comes to radiometric resolution. So every time an image is acquired or filmed by a sensor, its sensitivity to the magnitude of the electromagnetic energy determines the radiometric resolution. In other words, it measures the sensor to differentiate the smallest change in spatial reflectance or emittance between various targets. So this depends on various things. Sensors' ability to discriminate very slight differences in energy, or sensors' sensitivity to magnitude of the electromagnetic energy. So depend on various things, and also the saturation radiance and number of quantization levels. Those are the factors which base the radiometric resolution is based on. The radiometric characteristics describe the actual information content of an image. So every time the image is acquired on a film by its sensor, the sensitivity of electromagnetic energy determines this. So this represented with the selective power of 2. So assume like this, when it comes to certain levels of radiometric resolution, it can be said you need to measure something with a ruler. So you use a scale. One is calibrated with 1 centimeter interval, and another one is with 1 millimeter intervals, and another one is 0.1 millimeter interval. So when there's something you need to measure, you can use the rule with calibration of 1 centimeters only, so you can have an idea about that the measurements of that object with respect to 1 centimeter. So you can have an idea about, you can't have a certain idea about that object with respect to centimeters. So it has to be, should be able to have some have that idea based on another smaller amount of small unit. So radiometric resolution is such a thing. So when it comes to 2 point selected power, assume 2, so range correspondence, so 2 to the 2 is 4 bits. So when it comes, so there should be 2 bits to record the data. So 2 to the 2 is 4, so only 4 digital valuables are available. So you can, all the data ranges from 0 to 3, like as the all the data, all the measurements that you taken from that ruler varies from, let's say 0 to 2 millimeters, depend on the object. So centimeters. So when it comes to millimeters, you may have the idea up to millimeter 0.1 0.1 millimeters means you can have an idea up to smallest amount of so image such that like that. So image data can be displayed in gray tones according to this radiometric resolution. So 0 represents black, and also max value whatever when according to the bit value max value. So here 8 bits, max value is 255, it represents the white. So when it comes to 2-bit record of data, 3 is the max value, it represents white, such like that. So this graph may enlighten you a bit about how a bit varies according to radiometric resolution. So 8-bit means 2 to the power 8, 256 values with 0 to 255, and 10-bit 2 to the 2 power 10 to the power of 2, so 0 to 1023. 1024 is the maximum value then, such like that. So 1 byte represents 8 bits. Here's the gray tones, which varies from 8-bit when radiometric resolution is 8 bits. So maximum value 255 stands for white, and minimum value 0 stands for black. So here let's have a look back into our 4 types of resolutions. 3 types of resolutions have been discussed so far: radiometric, spatial, and spectral. So next type of resolution is temperal resolution. So before that, the radiometric resolution can be defined according to brightness value. It can be defined as possible brightness value of each band of data. So dn values are represented according to those bit rate of a remote sensing image. So 2-bit data is here. So for quantization levels, 8-bit data 256 quantization levels. So it's much clearer than this 2-bit image. So which one has the better radiometric resolution? You can have a glance and you can say this. The reason for that is there are number of quantization level is higher when it comes to whenever the radiometric resolution is high. So if you want to have an idea about these types of resolutions, so spectral resolution deals with wavelength of electromagnetic spectra, and then spatial resolution deals with the area, and this deals with the simply with the difference of a brightness level. You can say that. So resolutions of different Landsat different satellite system is given here for your additional knowledge. We can have a small discussion on these satellite systems if you want, so leave a comment if you're interested in here. So here again, radiometric resolution, you can see when it comes to 1 bit is there are only 2 gray shades, 4 bit there are 4 gray shades, 16 quantization, 16 quantization levels, so 8 bit and 256 quantization levels. So when number of gray shades are in a higher level, so intensity level can be detected by the remote sensing system. Here you also see 5 bit, 6 bit, 8 bit, 8 bit above all, 8 bit, and 5 bit. When we come to temporal resolution, it deals with the time period between two observations, so it deals with time. So this also to be relativity of the satellite. As I told you earlier, we will discuss again this on under the characteristics of satellites, and also we discussed a bit about this regarding scan lines on previous lecture. The capability of a satellite image, the exact same area of satellite is said to be the temporal resolution. So temporal resolution is with time. So if you say Landsat TM satellite, its temporal resolution is ought to be 16 days or something. So it means same position is measured through by the satellite for exact 16 days period. So assume that your house is observed by a satellite or it sends today at 6 p.m. and tomorrow at 6 p.m. So that sensor satellite temporal resolution is called 24 hours, 1 day. So 16 days of temporal resolution is defined in the Landsat satellite system. So it means its satellite repeativity, or it goes through the same area for 16 days. So its temporal resolution is thought to be 16 days. The length of time between repeat coverage, how long between two consecutive images, in other words, of the same area. So it's important, determined by the orbital period of satellite. When it comes to geosynchronized satellite, it's okay, you can decide temporal resolution, because you know what you don't have to worry about orbit. So but when it comes to polar orbiting or sun synchronized satellite sensors, so repeativity decides on the orbit. So one of the advantages of geosynchronized sensors is so you can decide the repeativity when you design the satellite. But when it comes to polar orbiting satellite, you have to decide it when you decide the orbit. So you can something like that. So multi-temporal images are desired when to land cover monitoring and progression of events such as disaster recovery, and duration of event is one of the key things which acceptable temporal resolution is dependent on. So temporal resolution tells how often your target is imaged, and according to the area you can see here, temporal resolution, how this 1972, 1982 and 1993, 1997, these are the years that these images take. This how this varies to over the years, the same area. So how the SWAT is calculate these additional things. Actually SWAT is what we call in spatial resolution. I forgot to mention that SWAT is the area or the area corresponded to on the ground is not the area, the distance corresponded to field of view is called SWAT. So it can be measured by using this equation, but these are not taking into concern in here. So that's it about resolution of a remote sensing image. So there are 4 types of resolution being discussed here: spectral, spatial, and temporal and radiometric, and there are so many additional things included in the slides I used here. So hope only we focus on the theory part, not the calculations. So Hope you learned something from this lecture series as well. Leave a comment and subscribe our channel. So share these videos and give us a feedback to improve this lecture series further. So have a nice day. Thank you.